So it can often make a lot more sense if we think about things in terms of energy. We've been discussing energy diagrams a lot in this class. It's a very good way to visualize exactly what's going on. So let's think of the energy of interaction when we're comparing atomic orbitals to molecular bonding orbitals. And what you find is when you have a bonding orbital, the energy decreases compared to the atomic orbitals. So you can see here in this slide, we have the atomic orbitals for the two hydrogen atoms. Each of them have one electron in them. Hydrogen has one electron in a 1s orbital. So if we look at the molecular orbital, that's actually going to be lower in energy than either of the two atomic orbitals. So it's going to be favorable for the electrons instead to go to that lower energy state and be within the molecular orbital. So let's draw in our electrons there. So we have our two electrons now in the molecular orbital. So anytime that you're drawing these molecular orbital diagrams, you want to keep in mind that the number of electrons that you have in your atomic orbitals, you need to add those together and put that many electrons into your molecule, right? We had one from each atom, so that means we need a total of 2 in our molecular orbital. And what you can see directly from looking at this energy level diagram is that the molecule that we have is now more stable than the individual atoms. That makes sense because we're lower in energy. The electrons are now lower in energy. So that's the idea of a bonding molecular orbital. Since we're talking about wave functions, since we're talking about the properties of waves, we don't only have constructive interference. We can also imagine a case where we would have destructive interference. Just like we see destructive interference with water waves or with light waves, we can also see destructive interference with orbitals. So let's think about what that would look like. So in this case, we would have 1sa and 1sb, and instead we would subtract one from the other. And what we would see is that instead of having additional more wave function in the middle here, we've actually canceled out the wave function, and we end up with a node. So we can also name this orbital, and this orbital we're going to call sigma 1s star. So if we name this orbital, this is an anti-bonding molecular orbital. So we had bonding, and now we're talking about anti-bonding. When we talk about anti-bonding, essentially we're taking 1sa, and now we're subtracting 1sb. And what we end up with, again, is sigma 1s. And the important thing to remember is to write this star here. So anytime you see a star, that means an anti-bonding orbital.